I'm Giorgia Zucchelli, Product Manager at MathWorks, and I'm really excited to be here at IMS on the exhibition floor and talk about antenna to bits. So with MATLAB you can model an entire physical layer of a communication systems, all the way from the digital signal processing down to the antenna, channel, including beamforming algorithm, RF systems, and more, you name it. In practice, how does it start? Well, you can just start using MATLAB and perform RF budget analysis. You can choose different components, different impairments, and stitch them together and analyze the chain. You can analyze the chain both with freeze and harmonic balance. Then you can generate a model for simulation. This means that from this model you can start integrating more and more components. In this case, we have a single chain that gets replicated 8 times to model a transmitter with 8 parallel channels. Then what's next? Well, if you're talking about beamforming, we need an antenna. The next step consists in designing an antenna. Here we use the antenna toolbox and the full wave electromagnetic solver of the method of moments to analyze a circular patch antenna, both for field, ports, and surface properties. From a single antenna, we move to an array of antennas, 8 elements, taking into account couplings, near field, far fields, you name it. And then, of course, we can integrate all of this in MATLAB with scripting, so you can automate the analysis and add more details, and then in our model. So you see here we have the 8 parallel chains together with the antenna array, taking into account near and far field coupling and polarization effect. What's next? If we talk about MIMO systems, we want to integrate beam steering algorithms. So what we can do is analyze the array using the array factor and pattern superposition and use different strategies to steer the beam. You can do analog beamforming, digital beamforming, you can do hybrid beamforming, phase domain, true time domain, you name it, all the algorithms are possible. Again, the strength of MATLAB and phased array system toolbox. From here, from the app, we can generate again MATLAB code and integrate our beamforming algorithm into our model. So you see how we layer step after step different levels of details in our behavioral system. So now we have added our phase shifter. And we can probe the voltage, the instantaneous excitation at the terminal of the antenna, which means that we can compute the pattern of our transmitter, taking into account nonlinearity, noise, coupling, dispersion. Again, you name it, it can be modeled. Next step, there is more. We can model the power divider, so the coupler at the input of our transmitter. So in this case, we just model it with an ideal Wilkinson splitter, but then we can also design the splitter using a PCB component, a corporate divider. Again, analyze it using full wave electromagnetic solvers and integrate the results in our system simulation model. Last step, you can simulate a standard compliant 5G signal through our transmitter. In truth, this is a standard compliant and test model 3.1 400 MHz signal, FR2. But it could be also a SATCOM signal, or it could be a Wi-Fi signal, you name it, different standards are supported. And here you see that we generate a signal, we look at the spectrum, look at the EVM of the reference signal, and of course it's the reference signal, so it's perfect, the EVM is 0, essentially we are happy here. Now we pass it through our transmitter model, taking into account all the effects that we were talking before, and we can look at the results and look at the spectrum. And then you might wonder, oh, the spectrum looks really terrible, so my EVM is going to be really bad, and I need to do lots of design and optimization of my transmitter to improve the performance. And here is really the beauty of antenna to bits. It allows you to assess, is this important or not? Because actually, when we compute the EVM, we see that the EVM is really good. Why is that? Because our 5G reference receiver also includes an equalizer, and it equalizes all the dispersive effects introduced by the channel. In this case, dispersion is introduced by the transmitter, so you don't need to spend lots of time in making the transmitter perfectly flat, because effectively this behavior gets corrected in the digital baseband domain. I hope you enjoyed this presentation. If you want more information, please look on mathworks.com, and thank you for watching.